Alright, so as I mentioned at the beginning, water is crucial for life. It is the signature that they look for on a planet to see if something could exist there. There's certain properties of water, they're very unique to it as a compound, that are particularly unique and necessary basically for the way life functions on a cellular level. And also there are also certain properties of water that have made the planet itself more habitable, in the way that it stabilizes the temperature of the planet, it's able to absorb and transfer energy around and that kind of thing. So one of the things is that it does have a wide temperature range. So good job, Group 6, that is correct. The 0 to 100 degrees, that is there's not a lot of substances that stay liquid during that over that wide of a range there. Liquid state is not really that common of a state in general. Most things are most things are solids. Most of the substances on Earth, compounds on Earth, are solid or gas, and then there are a few like water. Water is the most common type, which is a liquid, and it stays liquid. So not only is it at a wide temperature range in general, but it also happens to correspond to the average temperature of the Earth, because the average temperature of the Earth is around 67 degrees Fahrenheit right now. So that kind of puts it in the middle-ish, well, in the low end actually of it, but it keeps it in such a place, this area that water is usually liquid on Earth, but sometimes it's a solid, sometimes it's ice, and of course sometimes it's also a gas in the form of water vapor in the atmosphere. It has a very high heat capacity. That means it absorbs a lot of energy before its temperature changes. That is the big part of what makes it so good at absorbing and transferring heat energy and moving it around the globe. It's a very good solvent for ionic and polar compounds. Now, many of you got this one wrong on the pretest because you put nonpolar compounds. Oils are nonpolar compounds. An example of a polar compound would be sugar. Some proteins are polar and therefore soluble, some are not. Proteins are very complex molecules. Ionic substances are things like salt and other minerals, iron minerals, nitrates, phosphates, those kind of things that we also need in our system. So this is important because this allows us to bring in the substances like food and minerals and things like that we need, and other organisms too. But it also allows the substances, the toxic substances like ammonia and carbon dioxide and other things like that that could damage our cells to be flushed out of our cells as well. So that's one of the reasons why water is such an important part of cellular compounds and life in general. Now this last one is not really life-giving completely, because in a way it's a bad thing for life, because this is how you get frostbite, is the fact that water, when it freezes, it expands. It starts that expansion process around 4 degrees Celsius. So 4 degrees Celsius is actually the densest point of water, distilled water. Like anything else, water at up to 100 degrees Celsius before it boils, as you cool it down, it will get cold, it will get denser. And I want you to understand this, because this is part of another thing we're going to talk about with the ocean currents. So we'll get colder, we'll get more dense, okay? But then a unique thing happens at around 4 degrees Celsius is that it starts to arrange itself into its crystalline structure. And in order to do that, since it's a kind of a funny shaped molecule, it has to arrange itself and spread apart actually from the way it was when it was a liquid. So that's a unique thing. Most things, when they freeze, they get solid, they get more dense. And usually a solid substance will sink in its liquid form. In other words, you take a rock and throw it into lava, which is molten rock. That rock will sink because the solid form of it, the molecules and the atoms and everything are closer together. Water is not the case in that. And therefore it will expand, and that's why ice, of course, floats. Now, this is very important, of course, because of the fact that if that didn't do that, then the oceans of the Earth basically would freeze, theoretically, from the base all the way up. And so we'd have big solid blocks of ice in the ocean, maybe a liquid layer on top, but we'd have a lot less water available. And also in freshwater habitats like ponds and stuff like that, where it gets real cold, the ice freezes over on the top, and that insulates the lake underneath, and therefore it stays liquid and doesn't get too cold so that the fish can survive and make it through the winter, that kind of things. And people can do crazy stuff like ice fishing. Any questions about the properties of water that make it particularly, that's okay, important for life? This is properties, process, hydrosphere, unique importance of the water cycle, ocean currents, properties of water. So this is what we're looking at here, why water in particular is so well suited for life. All right. Okay, distribution. So this is just basically where we find water around the world. As I'm sure you probably know, the oceans hold most of it. They are the lowest lying parts of the earth. As we shall see, the reason for this is that the crust under the ocean, the plates that make up the Earth's crust, are heavier in the ocean. They're more dense, so they get sink down and they're lower. So therefore, consequently, when it rains and everything, that water runs out, and eventually all the water, all the precipitation, everything flows towards the ocean. And that also, of course, explains why the oceans are salty, because as it makes its way down to the ocean, it's dissolving minerals and other stuff along the way, and that's why it's salty there. And then also, if you were to take saltiness or salinity levels starting where the water precipitated up in the mountains or in a lake or something like that, it would get saltier and saltier as it makes its way down to the ocean. So that's why that is the case. Ice, most of our fresh water on Earth is frozen in ice. We are actually in what's known as an ice age. A lot of people don't realize this. They think of ice ages and, you know, the woolly mammoths and things like that, and the glaciers coming all the way down to the like the New York area and things like that. That's actually what's known as a glacial period. We're in an interglacial period of an ice age. And the reason why we're in an ice age is because we have persistent ice in Antarctica and Greenland and in the glaciers around the world where it does stay frozen. You do have that ice year-round. Okay, so we're actually in that. Based upon the fossil record and geological record and everything else like that, we should be going back into a glacial period in the next, who knows, 100,000 or 50 to 100,000 years. You guys don't have to worry about it, but we should be going back into that. So a lot of factors that affect that. So that's where most of your fresh water is. That water is fresh water for the most part. And then third, very important, is the aquifers or groundwater. I'll go ahead and give you the points for that. We're going to call it groundwater simply because technically the aquifer is really the rock that contains the water. So it's just a technical difference. Pretty much the same thing. People usually use it interchangeably. So we got groundwater. Simple term. It's underground. And we'll see later there's two different types of groundwater, really. And then you have your surface water. That's going to be your lakes and ponds, rivers, wetland areas, things like that. Fresh water, it's on the surface. And then finally you have the water that's in the atmosphere. Now this water in the atmosphere, we're still talking about liquid water here. This is the clouds. This is not water vapor. Water vapor is considered to be part of the atmosphere. This water that is in the atmosphere is the clouds. The clouds are actually liquid water. A lot of people don't realize that. Just like steam, when you see steam rising up, that's actually liquid water that is condensed. Water vapor itself is invisible. You can't see it. Okay. And so these are the areas. And then this water, because of the boiling point of water and the condensing point of water, etc., which is the same thing, that water is going to change phase regularly on the Earth, evaporate, condense, precipitate, flow, soak down in or infiltrate in the ground, make its way back to the ocean, start the whole process all over again. Of course, it's not just the ocean where evaporation occurs, but most of it does. And so all these different processes in the water cycle are the way that the water moves around these different areas between the ocean and the groundwater and the surface water and things like that. And that's an important process, not only because of heat distribution. It also produces fresh water. You know, that's every terrestrial organism needs fresh water, not just salt water. So you know, we can't survive on salt water, and plants, etc. as well. So the source of that is the water cycle. As the water evaporates, it comes down, of course, as fresh water. And then it also, that's one of the other ways besides ocean currents that the heat is distributed. So when the sun's energy hits the earth and that water evaporates, it takes that energy with it when it evaporates, absorbs the energy, goes up in the upper atmosphere, condenses, and then releases that energy. So it's not like super hot at the surface and super hot at the equators and stuff. It makes it even all the way around. Then, of course, it forms our lakes and rivers and groundwater and all those other kind of things. Any questions about the distribution or the water cycle or anything like that? Okay, you're going to need to know the water cycle pretty thoroughly as far as the different parts of it and what the different actions mean and everything. So I got a diagram for you to see in there. And then finally, ocean currents. You have two types. And one is a shallow surface current. These types of ocean currents have been known for centuries, ever since people have been sailing. And they are driven by the wind. So the wind takes certain patterns, and that's something we will look at when we look at the atmosphere, based upon the way the Earth is heated and the spinning of the Earth and other kinds of effects. And as it blows across the ocean, it pushes the surface with it. And of course, it continues along with that, of course, but the difference being between the wind currents and the ocean currents is the continents. Because once those ocean currents hit a continent, of course, they're going to loop around. So for example, there's a natural, what we call trade winds, going from the east to the west along the equator. And that pushes our Gulf Stream along. That's what pushes the waters that are off of equatorial Africa towards us. And that's also what brings along our hurricanes. As the hurricanes, you may hear that they are formed, or they predict how they're going to be based on the rainy season in Africa. Those storms come out of Africa, they get over the ocean, and if they have a chance to build and everything, they may become a hurricane. So that wind blows along that way. It's the trade wind blows along, and it blows the water that's underneath it. That water that's underneath it's the Gulf Stream. But then the Gulf Stream comes up into the Gulf of Mexico, wraps around through the Caribbean, wraps around us, flows back up the eastern seaboard, and ends up going over towards Europe. It sinks in the colder waters there, and part of it goes down and sinks and becomes what we call a density current, and then part of it actually stays on the surface. It's one of the few that has a continuous surface current to it that's not doesn't completely sink down and everything. So those are the surface currents, and they're common throughout the world, but pushed by the wind currents. But other currents, the currents that actually move more water, that have only been really recently discovered in the past 75 years or so, 75 to 100 years that we've been able to explore the depths of the ocean, things like that, are what we call density currents. They are driven by differences, what we call the thermohaline differences. Sorry, group 2. So salinity actually was already up there. Haline is another term for salt. And so you have two main factors that affect the density of water. One is temperature. As I mentioned earlier, water, when it gets colder, does condense. It does get heavier to a point, to about 4 degrees Celsius. But it also will get denser if it gets saltier, and that will occur through evaporation typically. So both of those together combine, and when it gets denser, it just sinks right down, and it's got water behind it that's sinking, and basically pushes it along and tends to flow along the ocean floor. I'll give you some, I'll show you some diagrams and everything like that. So it'll flow along the ocean floor, taking a lot of that energy and things with it. But not only that, it will also, as it goes through the ocean floor, pick up a lot of nutrients. Because what's down there on the ocean floor? A whole lot of what? Fish and marine poop, organic waste, detritus, feces and dead organisms, things like that. All kinds of nasty, yucky stuff. But great fertilizer for plankton and planktonic algae. And so what happens is these currents will move along down the ocean floor and maybe hit a continent somewhere, like the Southern Pacific cold water current goes along about down around Antarctica, and then it comes up along the coast of South America around Peru. And there happens to be very extensive and profitable marine fisheries there. They do a lot of commercial fishing in those areas, things like that, because it supports a lot of sea life where that happens. So that's an important thing for life. So that's one of the things you need to look at with all these. We're talking about physical things like currents and evaporation, all that kind of stuff. but they have an importance for life. So make sure you're looking at these things with why does it matter when it comes to living organisms on Earth. That's one of the things. Not only does it make the whole Earth, more temperature equivalent between the poles and the equators and things like that, but it also transports nutrients. Same is true of the wind patterns, as we'll see. They carry things like pollen and dust that may seem like a pollutant, but it's actually a fertilizer for a lot of stuff and things like that. So, so you have your shallow surface-driven currents or wind-driven currents, and you have your deep density-driven currents. All these things move around. Most of these systems will go along the surface for a while, and then they'll get the more dense and sink, and then they'll go along, and then they'll come back up, and they'll come back up to the surface and get pushed along again. This whole system of interacting currents are, I'm sorry. The ocean energy conveyor system. So that moves energy around the world. Not only that, it also brings water vapor with it. So, for example, you're probably familiar with the fact that London is very rainy. It's cold. It gets cold enough. Not as cold as other things that are along the same parallel. If you look at where London is, or England is, or Great Britain, whatever you want to call it, it's in the northern latitudes where northern Canada is, Siberia, etc. Much colder areas, but it's warmer because of the Gulf Stream, because it's that warm water, so that brings warmth along, and it also, as you may know, is very rainy, and that's because that warm water current's got water vapor above it, and the fog that comes in London's another example of that. So these ocean currents have a very direct impact on the type of climate of the areas that they pass by. Okay. Questions? Anybody? About properties of water, the way it's distributed around the globe, and the way it moves through the water cycle, or ocean currents. These are the main topics we'll be studying in the hydrosphere. All right. So.